our last video, we looked at electric potential energy, which happened when we moved a charge in an electric field or applied an electric force to a particle. Now we're going to look at what's called electric potential. And even though the words sound pretty similar, when we're not using the last word energy, we're kind of talking about something analogous to when we're talking about the electric field versus an electric force. Because the electric potential is what we have when we take electric potential energy and divide it by a charge. We get the electric potential. So the electric potential energy is a specific amount of energy, and then we divide it by sort of a hypothetical charge that could be experiencing that amount of potential energy in a given environment. Just like with the electric field, we took an amount of electric force and divided by a hypothetical test charge in order to get to something that could feel that effect of the other agents in that environment. We use the letter V to represent the electric potential, and that's primarily because of the fact that it's related to voltage. And in fact, we measure it in volts. And if you look here, if we have the units joules for the potential energy and divide it by coulombs for the charge, 1 volt, the units for the potential, is 1 joule divided by 1 coulomb. And you already have an instinct for how much 1 volt is, because we do use volts in sort of our common language, like a 9-volt battery, for example. So here is an example of how we can apply electric potential in an environment. So this has 3 charges distributed. Here's a positive and a negative charge. Now these are source charges. So we're going to think about the placement of hypothetical charges that could be in this environment. And at different positions in this environment, we can think about the potential. And so just like if we're looking at a topographical map of the elevation in an area, these dashed lines represent a constant potential, whereas on the topographical map they'd be constant elevation. So this is an equipotential. Everywhere on this line is the same potential. So this is 20 volts, and here it's 40 volts, and this circle is 60 volts, and that one's 60, and this is 0, and that's negative 20, and so forth. And you can see pretty obviously already, as we go towards a positive charge, the potential gets more positive, and if we go towards a negative charge, the potential goes more negative. We can use this to solve an energy problem. And we do that by thinking of what happens when we place an object charge that actually experiences the potential energy when we put it in this potential. So let's say we have a proton. We started at A and it ends at B, and we want to know how fast it is going by the time it ends at B. So this is a conservation of energy problem. So the final energy is going to equal the initial energy. So we have the final kinetic energy plus the final potential energy is equal to the initial kinetic energy plus the initial potential energy. The initial kinetic energy is 0 because we say we release it from rest. And so the final kinetic energy is going to be equal to the initial minus final potential energy. We can plug in the equations that we know, 1/2 mvf squared for kinetic energy. And if we look up here, we have the equations for the potential, the electric potential energy. So we have a Q times the initial potential, it's starting at A, minus the charge at B, or the potential at B. We're trying to solve this for V. So we're going to have 2 times Q VA minus VB all over M. And now we can plug in the units, or rather the numbers with units. So we have 2. The charge of the proton is 1.60. That is a typo, actually. It's 1.602 times 10 to the minus 19 coulombs. Voltage at A, we can see, is 60 volts. And the voltage at B is 0 volts. We can follow this around there and see that is 0 volts. And then we divide that by the mass of the proton, which is right there, 1.66 times 10 to the minus 27 kilograms. And then all of that comes out to be 108,000 meters per second. Sorry, you can't quite see that, can you? So the electric potential is related to the electric field, and there's a few rules that we can use when we're drawing the relationship between them. For the first very important rule is that the electric potential lines will never touch each other, because that would mean that the electric potential has more than one value at a given point. So equipotentials can never touch. Equipotential lines are always perpendicular to electric field lines. So if we have a bunch of equipotentials and we wanted to draw an electric field, then we would know that they have to be at right angles to each other. It's always pointing from the positive towards the negative potential. Let me say that again. The electric field lines and vectors are always pointing from the positive potential towards the negative potential because they're going in the directions that a positive charge would want to go. And finally, the equipotential lines are closer together where the electric field is strongest. So if we wanted to put that together here, we could see that, for example, right here, this would be a very strong electric field, but over here, the electric field would be pretty weak. And then over here, the electric field would be very strong, but it'd be pointing towards the negative. In fact, if we wanted to draw it here, we'd have to cross the negative. That doesn't mean a positive charge would go past the negative charge. It's just showing how strong the vector is. Let's give an equation for a specific one. If we had a single point charge, so let's say this is a single positive point charge, so like a proton, the equation for that would be K, and remember K is that electrostatic constant that we had before, 8.99 times 10 to the 9 coulomb meters squared per coulomb squared. This was in newtons. Newton meters squared per coulomb squared. Q is the charge of the source. R is the radius away you are. So if we were to draw equipotentials, they would start close as you are close to the charge, and then they would get farther away. And they would be circles, but you know, drawing circles is hard. And if you had more than one of these, you would just add them together, just straight add them together. If you had a potential map and you wanted to find the amount of electric field at given points, what you would do is you would take the amount of change between equipotential lines and divide that by the distance between those potential lines in the direction that's perpendicular between the lines. This is technically a kind of derivative that's called a gradient. At least it's an approximation of that kind of derivative. And there's more than one way to do an approximation like this, since we can't get an exact gradient without knowing the basically the equation for this this map. But there are better and worse ways to do this approximation. We're just going to do some sort of approximation, and that will be good enough for what we want to do. So let's do an example of that. So first, let's just see what the field lines would look like at each one of these. So first we can see that the positive potential is on the bottom left and the negative potential is on the top right. We don't know what source charges made this potential map, and it's kind of none of our business. This potential is here now. We do see that the y direction is in meters, the x direction is in meters. This is real space that we're looking at. And the potential map is just being measured in volts and along these contour lines. So if we pick these different points, we can see what the potential would look like at these different points. So for example, C right here, we would want to draw a line that's perpendicular to this, pointing in the negative direction. B, we'd want to draw a line that's perpendicular. These lines are closer together, so we'd want to draw a bigger vector than we did down here. So this is the electric field at B. This is the electric field at C. Now there's no reason that I drew it exactly this long for C. I just picked something. But I do need this vector to be bigger than that vector. For D, is this one bigger than that one? Maybe a little bit. So these are a little bit closer together, so we can make that one a little bit longer, but not that long. All right. So this is the electric field at D, and it is very obvious that these lines are much farther apart than any of these were. So the electric field at A is going to be very small. And now let's actually calculate the value at a given point. This is just going to be an approximate. And we'll do it at C here. And in order to calculate that value, we need an approximate measure on the scale of the distance between these lines. Because remember, the magnitude is equal to delta V over D. This distance is D because it's the distance along that perpendicular direction between the field lines. Delta V is the change in potential between these two field lines. So in order to try to get an approximate measurement of that distance, I'm just going to use this paper, and then I'm going to hold it next to the scale, and then, so I figure that's about 3/4 of that scale, so 3/4 of 0.2 is 0.15. So we've got delta V, so each one of these is going 50 volts, right? Because every 2 is 100 volts. So this is 50 volts divided by 0.15 meters, and we can quickly calculate that is 333 volts per meter. Now you might think that's weird. The electric field in volts per meter, but before our units were newtons per coulomb. Right? Well, what is a volt? A volt is a joule per coulomb. So we're going to multiply that by 1 over a meter. And a joule is a newton meter times 1 over a meter. And you can see that a volt per meter is the same as a newton per coulomb. So they do have the right units. Volt per meter, newton per coulomb are the same unit.